So let's think about some properties of Schrödinger equation. And most important one is so-called linearity and superposition. So Schrödinger equation is linear, and what this means is, like in the equation, you only have psi and no psi squared, psi cube, or psi something like that. None of these terms exist, right? Only the linear term is there, so the equation is linear. And therefore, if psi 1 and psi 2 are solutions of Schrödinger equation, any linear combination of this, like let me call it A psi 1 plus B psi 2, is also solution. And it is a solution of full Schrödinger equation, right? Let me say it like solution of, so far we have time dependent Schrödinger equation. So we have to be careful for that. So now let's look at this from the perspective of like our like double slit experiment. So in the double slit experiment, so we have, like here is our double slit. Maybe this is slit number 1, and this is slit number 2. And we are shooting electrons, like we are sending the wave, right? And let me call this, so this one is slit number 1, and this one is slit number 2. And I can like think about closing one of the slits and looking at the pattern on the screen. And like suppose I close this one, slit number 2 is closed, then there will be like a wave function on the screen, maybe something like that. And I'm assuming the slit width to be very small. And as you know from our previous discussion, the slit separation should be of order of wavelength of the wave. Otherwise, you don't see the significant effects. But at the moment, if I close this slit, I have this one. Let me make this blue. And if I close not the first one, but not the second one, but the first one, I'm going to have something like that. Maybe in the second location, let me make this green, right? Something like that. So only one open. We have, so this one, psi 1 squared. Probability to hit a point on the screen is psi 1 squared. Only 2 open. That means probability to hit a point on the screen is psi 2 squared. And finally, I open both of them. If both 1 and 2 are open, what do we have? The wave function is psi is equal to psi 1 plus psi 2, and probability is absolute value of psi squared And this is going to be psi1 star plus psi2 star psi1 plus psi2. Also, let me call these objects 1 and 2 classical probabilities if you want, or quasi-classical probabilities. So I open this up, I will obtain psi1 squared plus psi2 squared plus psi1 star psi2 plus psi1 psi2 star, or let me write it the other way, psi2 star psi1. Right? And this one is P1 plus P2, then P12 is not equal to P1 plus P2. Right? So that's the important difference, which may look trivial, but this is what we call, because without this term, we wouldn't have any interference on the screen, right? For us to be able to have the interference on the screen, we have to have this term. Then I am going to call this term interference term, because this is the responsible term. Interference term. Any questions?
Can you explain that part is not equal to P1 plus
So, because when both slits open, the wave function is this, right? And probability to hit a point on the screen is absolute value of absolute value square of the wave function. And if I do that calculation, I have absolute value of 1, absolute value square of 2, plus an additional term. And from the presence of this additional term, I know this P12, okay, this is P12, is not equal to P1 plus P2 because of this additional term. Then I say, okay, the reason for having the interference on the screen should be this term, because without that, I would just have this classical, like the combination of this blue and green line. Good. Any questions or comments? So let's think about observables. So this may be a new terminology for you, but don't be scared. Observables and expectation values. So once, okay. Once psi is obtained, everything else, all physical quantities can be obtained from psi. If you want, psi is the most fundamental description of nature in that sense. And because psi is a probability, for example, I can think about, so the expectation value, like let's think about first probability, right? There is like some discrete variable E, and if you sum over all values of this discrete variable, you need to have 1. So this is normalization in probability. And if you have like some quantity you want to observe, you can think about its expectation value, right? A that depends on I, and you are going to be like probability to observe I, the value of I divided by sum over all I, right? So this is normal probability. There's nothing fancy about this. And we are going to like adopt this description to quantum mechanics by using the wave function. For example, if we want position, so expectation value of position is going to be, because we have continuous values, we have to have integral, not the sum. And here is the x. And here is the probability to observe x. And I can normalize the x. But if you already normalized, if this psi squared is 1, you can just have the numerator and you can drop the denominator because you already have 1 there.
Position x is equal to?
So this is the expectation value of x. So if you want, this is like kind of like an average value in the probability sense. If you measure x, your likelihood of finding x is given by this expression. Right? So if you have, like, for example, other objects, like, for example, any other function of u, let me not say u because we used u for something else. Let me call it f of x. Any function of f can be obtained similarly. So there's nothing different.
Oh, now it's okay. I thought that x is multiplication.
No, not multiplication. Yeah, this is like the variable x. Okay. But if you want to get, for example, momentum p, you cannot do that, right? If you, like, for example, let's try to write it and see the problem. So let me. So this is p, right? Okay, this is derivative. And I can, since this is an operator, I can take it outside the integral, and then if I hit something like this, right? I can, so because okay, I cannot take it. If I take it outside, it is acting on 1, and derivative of 1 is going to be 0. So this is kind of nonsense. And I think there is no way of justification for this. It is just how things work in this theory. So what you need to do is, like, you should split this, like psi star of x, take this p in the middle, and write the psi here, so that this p operator is acting on here. Okay, so that is how you calculate expectation value of p. Yes.
Here, P is just some. What is P first?
So in the first hour we saw what p was, right? In the first hour we identified p. Like, if you want, let me use this arrow notation. We identified p with this minus I h bar del del x. In that sense, if I take the derivative of an integral which is 1, it is going to be 0. That's why that derivative should be in between psi star and psi to have like a meaningful result. Yeah, now from this p, we are going to generalize that, right? Because the expectation value of p does not work like that, then we are going to say, look, this is not the proper way to define expectation values. Then we better have this thing, and also for x, we have to do exactly the same thing. And we put hat on the quantity to remind us it is an operator. It is going to act on the wave function. Moreover, even if you have like a complicated object that's a function of not only x or p, but also a combination, let me call it a function of x and p, and you can put it in between. So that's the rule if you want, g of x and p. Right? Yes?
How can you get a different number than 1 in the denominator? If you define the between.
So which line? This line?
Yeah.
How can we get a different number? So here?
I mean,
Yeah, the denominator. Yeah, it is generally 1, but if you forget to normalize, it's a good way to make sure it's normalized. Yeah, it is just 1 for normalized wave functions. But generally, we forget to normalize the wave function, then this one is a little safer expression to calculate expectation values. You're right, you can put 1 if you are careful. Yes?
All of these equations are
What is what?
All of these equations are between 0 and 1, right?
All of these equations are between 0 and 1. What do you mean? Like the expectation value of, for example, like it depends on your problem. For example, if I have like a free particle, x can be minus infinity to plus infinity. Or if I have like, for example, a particle in like a potential, it is likely to be where the potential is. If I have like a potential like a box, it's likely that the particle is going to be between the boundaries of the box. We'll come to that. Right? So the rule is then, let me summarize. So for momentum, let me start from position. So position is, we put like an x, but if you hit psi of x with x, it just gives the argument of psi, which is trivial. Momentum, so p is equal to minus I h bar del x. I think the easiest way is to memorize, like I said, exactly the way I expect you to memorize Schrödinger equation. I expect you to memorize this P2, right? P is equal to minus I h bar del x. I think for the quizzes, you can look at your textbook, but for exams, I expect if I ask a question, I expect you to be able to write this. I think which is no-brainer, but I think just if you look at it for long enough, you will remember. So energy, so E I h bar del t. If you want kinetic energy, let me use this notation from your book, is going to be minus h bar squared over 2m del squared over del x squared. And these are all for like one-dimensional problem. There is only x, and if you have x, y, z, for example, you just add y and z components here. And for p, you are going to have px, py, and pz. Each component is going to have its own momentum. So now let's derive time, so-called time-independent Schrödinger equation. So let's first write the Schrödinger equation. I h bar del t psi of x comma t is equal to minus h bar squared over 2m del squared del x squared plus u of x comma t, and this entire thing acting on psi of x comma t. And I say, like, suppose if u of x comma t only depends on u of x, that's the name, that's the meaning of this equation. So that means you have a potential is independent of time. Then x and t are separable. What this means is you can write psi of, let me use this uppercase psi here, like uppercase psi here, and you can write uppercase psi of x comma t as a product of two functions, which is lowercase psi of x times, let me use phi of t. So my claim is if your potential is time independent, you can do that. And let's see how to do that. So I'm going to copy this equation, and whenever I see psi of x comma t, I'm going to just paste this object, right? So this is like that, and so this one I'm going to paste that. And now I see, like, for example, so here there's no more t because that's the assumption, right? I assumed it is time independent. Now, okay, I have two derivatives, right? So this side, let's duplicate and see how to manipulate this thing. Maybe here. So first, this derivative is going to act only on t-dependent things, right? This is psi, it doesn't know about t, so I can carry this outside. So I can carry this outside like that, and I can think about this derivative acting on only on t-dependent things. Good? So that's the first step. Similarly, there is like a second order derivative here, but it is only an x derivative, and I can say that, okay, this derivative is only going to act on psi of x, right? Because that's what the derivatives do. They know about only x. So carry this object to here. And also, I shouldn't forget to put it here, right? Because there are two different terms like that. Any questions so far? And now I divide both sides with psi of x and phi of t. I divide phi of t, psi of x, and divide phi of x and psi of x, phi of t. And I cancel this. Cancel that with this, cancel that with this. Let me copy this and simplify. This is like that, clear this. This is 1. So this is gone, this is gone, this is 1. Now I see this side, and I only see t, right? There is no x. This side doesn't know anything about x. So this is only t dependent. And I look at right hand side, and I don't see any t, right? Everything is like written in terms of x. So only x dependent. Then left hand side is a constant for right hand side, and right hand side is a constant for left hand side. And we should better give this constant a name, and a reasonable name would be e, right? Then let me write this equation. So this equation is equal to e. That means I can just carry this guy to here, right? And this is a first order equation, right? And I think everybody knows how to solve this. How many people know how to solve this? First order derivative. You won't have simpler things than this, right? If you want, you can take I h bar here and take phi here, and it is derivative of phi divided by phi, and we know this is going to be log, right? Okay, this is gone, and right, like log of phi of t is going to be minus I e over h bar t times a constant, right? Then phi of t is going to be, just take this, e to the minus I e over h bar t. So time, so the equation is separable, one thing, but also the time component is trivial. It is like an e to the I t form. Then now I can put that exactly the same thing here, right? So let's copy this side. So this thing is also equal to e. Then I can take this object to here. And I can now delete the parentheses. And this is an important equation, so let's box it in. And this is time independent Schrödinger equation. Okay. So I think it's not too much to ask for you to be able to write this. If you can write time dependent equation, you can write time independent Schrödinger equation too, because it's the same thing. You just, rather than putting I h bar del del t, you just put e. And now, for example, free particle means u is equal to 0. If u is 0, u is independent of t. It satisfies like the separability condition. And in that case, the solution is also trivial, right? minus h bar squared over 2m del square del x square psi is equal to e psi, and it can be solved with e to the I kx or e to the minus I kx, where k is given by 2m over h bar e, right? Yes.
Can you go up a bit?
Yes.
You said this equation was time dependent, right?
This is time independent, right? This one in the box is time independent, and the previous Schrödinger equation, which we started with, so this is time dependent because there is time here.
So what if can we have an equation which only is dependent on t, like there is no x?
Yeah, there is. We wrote that equation too, right? Here, we separated, and right, this equation only knows about t, right?
So we have three equations.
Yes, we have three equations, but t. So we have to like quickly get to difficult part of the problem, right? And these are the easier parts. So we immediately just in 10 seconds we can solve this equation. You are right. There are like three equations, but like this one is trivial. And once you solve time independent Schrödinger equation, time dependent part is like trivially here. So the difficult job is going to solve this problem. Any questions?
So when we use each of these equations depends on our situation, right, or our conditions.
So what will happen is like now, like we'll generally consider time independent external potentials, right? In real life, for example, this room is a box and the walls of this room are not moving, right? Or the chair I am sitting is not moving. So there's an external potential, and inside this external potential, I put like a quantum particle and I try to describe that. So the problem will be, give me what u is. I'm going to find psi, and from psi I'm going to calculate all observables. And this will be the name of the game. And that will be the challenging part, because given u, we are supposed to solve a second order differential equation. Right now there's only x, and it should technically be d dx because there's no partial derivative. But if we had like y and z components, we would add partial derivatives here, and it would be a Laplacian rather than del x squared. We'll come to that too. Any questions or comments? Yes? Massless particle, like as we have seen previously, are by definition relativistic, and relativistic particles cannot be described with p squared over 2m. And I don't think anybody in like 4-year undergraduate equation will have to describe quantum mechanics of a massless particle, because it's very technical. It requires so-called relativistic quantum mechanics, and you'll have to learn so-called field theory for that. So maybe in 4th year people will show you a little bit of that, but for the moment, that's a very difficult subject for you. If you are interested, you can keep reading and learning more. So I think that this solution is also trivial, right? Free particle, I know like this. If you don't know how to obtain this, just substitute here. Right? First derivative is going to give me ik, and second derivative is going to give me minus k squared. And from here, I'm going to have E is equal to minus k squared times minus h bar squared over 2m. Then it's going to give me E is equal to h bar squared k squared over 2m. And from here, I also see the de Broglie, right? P is equal to h bar k, because this is p squared over 2m. And what was de Broglie? De Broglie was h over lambda, right? I think, do I have like okay, let me, yes, I think this is correct. There's like a 2 pi, you can multiply and divide by 2 pi, and 2 pi over lambda is going to be k. So if no other questions, I want to solve you the simplest and most important problem which you will see it's like really simple. And I think sometimes people use the name of this problem as an adjective for easy problems. Okay. So it is, let's solve particle in a box. And I will finish it there. Because it's like so simple, I don't think it's going to take too much. So what we said is like you need to give me U so that I can write down the time-independent Schrödinger equation and solve it. And for a particle in a box, U is given, U of x is given to be 0 if x is inside a box from 0 to L, and infinity otherwise. Just like this room, we are thinking about a box. So here is my box. So this is x is equal to 0. This is x is equal to L. So this is x. So this one is U of x. So here I have infinite potential. Here I have infinite potential, and my particle can only be inside the box. So then the proper boundary condition yes. So infinite potential, U is equal to infinity if you are outside the box. That's the meaning of infinite potential.
How do we get infinite potential?
In real life you don't, right? So that's an approximation. But sometimes we do this, like we want to model the nature, but like the correct description of nature is in general very complicated, we cannot solve it. So we do approximations, and this is like a common approximation. So you can put it in a very large potential, but even very large potential is not infinity, right?
Why do we think a particle can't be in infinite potential?
Why do we think a particle can't be?
Yes.
No, this is what we are thinking. We are thinking about a particle in an infinite potential. But in real life, there is no infinity, right? And the boundary condition here is because U is infinity at x is equal to 0, I expect psi of x is equal to 0, and also same way psi of x is equal to L to be 0. Good? Any questions? Because it's infinity, right? If there's like an infinite potential, there's like zero, like think about like a wall. And you are here. If wall is too high, you have like smaller and smaller probability to be here. If wall is infinity, you have zero probability to be here, even in quantum mechanics. Okay? Now the Schrödinger equation, minus h bar squared over 2m d squared dx squared. Because this is time independent, I'm writing time independent Schrödinger equation, and it is psi of x. And I want to, okay, let me duplicate and manipulate this equation. So this is going to be, I'm going to take 2m here, erase this, and I'm going to divide h bar square and like this. And I'm going to write, okay, there's like a minus sign, I don't want to miss it, it's going to be here. And you can see I can now even simplify that, like second derivative is equal to, okay, let me not erase that. Let me take this guy. And because E is positive, right, energy is, we expect it, E to be positive. So I define this to be k squared because of positivity, and I write k squared here. And this is the differential equation I need to solve, right? And typically, like how do you solve differential equations? People are going to show you ways to solve differential equations. They are like very technical ways. But the fact of the matter is you just substitute, right? You know the solutions, you substitute. That's how we solve the differential equations. And the substitution I'll do is like a sine of kx plus b cosine kx. Why do I think so? I know if I substitute sine, first derivative is going to be cosine kx, there will be a minus, and second derivative is going to minus k squared cosine squared kx. So this satisfies exactly the equation I'm looking for, and I can do exactly the same thing. Cosine derivative sine, right? Minus sine, and minus sine derivative cosine, exactly the same equation. And if sine and cosine satisfy my equation, from the linearity, a sine plus b cosine is also a solution. And I'm writing the most general solution. So then my most general solution is this. But like I said, we are trying to solve a differential equation with the boundary condition. Right? We are not done yet. To put the boundary condition, I need to put psi of x is equal to 0, should be 0. And I put here psi of x is equal to 0. I have a times sine 0 plus b times cosine 0. I know sine 0 is 0, so this side is 0. But cosine 0 is 1. And this thing should be 0. That means b is equal to 0. So I eliminated one arbitrary constant from here. Is that clear? Any questions? So what remained is, so this guy is dead. It did its job, thank you. So we just dropped it. So what remains is this part. And this part should also satisfy the second boundary condition. Second boundary condition is what? Psi of x is equal to L should be equal to 0. And this should be equal to A sine k L. And so A is like an arbitrary constant. The only way I can have this thing to be 0 is k times L should be n times pi. Otherwise, I cannot satisfy this boundary condition, right? No, n times pi, right? Sine is 0, right? In the circle, sine is 0 here and here. Good. Then k should be pi over L times n. Good. So problem is solved. Then my psi of x is now equal to, so a times sine n pi over L times x. Now what I need to do is normalize. So this is 1 should be equal to a squared. So I'm assuming a to be a real. It's just an arbitrary constant. Dx sine squared n pi over L x. And the integral limits are from 0 to L. Unfortunately, we have to take this kind of integral. How many people know how to take the integral of sine square? It is not hard. You just need to use this cosine square x minus sine square x is equal to cosine 2x. And once you write this in terms of cosine 2x, you'll see like sine and cosine, everybody knows the integral, right? Integral of cosine is sine, integral of sine is cosine. And at the end, you can find what a is, and a is going to be, so this is exercise I expect you to do. This is going to be 2 over L. Then psi, now you can see I have like numbers in my solution. It's like n of x, and the solution is like 2 over L. The normalized solution is sine n pi over L times x. And the corresponding energy, like we wrote above, so the k was equal to 2m over h bar squared E. Then, and we found k to be n pi over L, this means my E is going to be h bar squared pi squared over 2m L squared times n squared. Right? This is exactly what we were doing, these waves, and like we were trying to fit. At the end, we also found these discrete energy levels. Any questions or comments? Let me just draw you the solutions and then finish it there. So let's draw both wave functions and probabilities, and I'll be done after that. So this is psi from 0 to L if you want, all of them. And this is psi squared. So the ground state is like n is equal to 1, right? So this is n is equal to 1, 2, 3, dot, dot, dot. So here's the ground state. Something like that. So this is n is equal to 1. Here's the first excited state, the second minimum energy. So this is n is equal to 2. So you can see there's like a node here, and third excited state, n is equal to 3. I have 1 and 2 nodes. And if I look at the probability, you can see probability is going to be something like that. So for the ground state, classical probability seems to be maximized in the center of box, which is reasonable. But for the second, right, you can see there's like a 0 probability to find the particle in the center. This is a quantum effect. And for the third one, yeah, something like that. And if you remember also, like the minimum energy was also non-zero, which was also a quantum effect, right? Okay, I think this is the end. You are responsible until this point. So I think I'll continue your question how to get like the observables from this next time. How to get the expectation value of x, how to get expectation value of p, how to get probability from x1 to x2. But in the exam, everything until this point is included.